Namaste. Welcome to Indian Knowledge Systems Primer Course for Children. In this session, we will look at algebraic identities. Ancient Indian mathematicians have divided foundational mathematics broadly into two categories. They are Vyakta Ganita or Pati Ganita, which is the arithmetics, and Avyakta Ganita or Bija Ganita, which is the algebra. Now, let us try to understand the word Vyakta Ganita. It is made of two words, that is Vyakta and Ganita. Vyakta means clear, known or manifest. We already know Ganita means mathematics. So, what does Vyakta Ganita mean? So, the arithmetic problems which deals with the numbers that are expressed directly, and the problems of geometry where the measure of the geometrical figures are known, and problems that involve performing operations on known quantities. These all fall under the Vyakta Ganita. Hence, Vyakta Ganita is foundation in mathematics. Next is the Avyakta Ganita. We saw that Vyakta means known, right? So, Avyakta means unknown or unmanifest. So, Avyakta Ganita is the branch of mathematics that deals with some unknown quantities. Then how do we get the values of these unknown quantities? They can be deduced based on some given conditions. So, for these conditions, not just one value, but then it can be satisfied by different values. That is why they are called variables. To represent variables, various symbols are used to form expressions that represent the conditions. These expressions are called equations. It has been very evident that Indian mathematicians had known well and utilized these algebraic identities. This we can see in the work called Aryabhatiya, which was done in 499 CE by Aryabhatta, who was born in the time 476 CE. There, in his work, he has clearly stated the relationship of various algebraic identities. The geometric demonstrations for these identities have been given in many other works, such as Ganita Yukti Bhasha, that was written approximately in 1530 CE by Jyeshtha. Then Buddhi Vilasini, which was written in 1545 CE by Ganesha Daivagnya. If you remember, we saw few of the demonstrations of Ganesha Daivagnya in the previous session. The next text is the Kriya Kramakari, that is it was written by Shankara and Narayana in 16th century CE. These are some of the commentaries. Note that the works like Aryabhatiya and Leelavati are all in the form of poetic verses, whereas these commentaries are in the form of prose, where they give more examples and demonstrations. Now, when you hear the word algebra, this equation pops in your mind, right? A plus b the whole square is equal to a square plus b square plus 2ab. This is a well known and common formula that all of us know. Jyeshtha in his work has given a geometric demonstration to prove this equation. Let us see how. For that, you will have to take a square of length, that is a plus b. So, we see that the length of a side is the sum of two values, that is a and b. Now, we know that the area of the square is a plus b the whole square. Now, in the next step, we are going to split the length a plus b as a and b. So, this would be the length a and this would be the length b. Here, this is a and this is b. So, what are we going to do now? We are going to draw two lines like this. Along the two sides. So now we see that we have got 4 segmented areas. That is, we have a square here, we have another square here, we have a rectangle here, and we have a rectangle here. Now we see that we have got 2 squares here, right? So the length of this square is A. So the area would be A square, and the length of this square is B. So the area for this square would be B square, and we have 2 rectangles here, right? So which has the sides A and B. So what is the area of a rectangle? It is the product of 2 sides, right? So which will be AB. Again here we see that this length is A and this is B. So the area of rectangle becomes AB. So when we add this together, we see that we get A square plus AB plus AB plus B square, which gives this value. Hence, this is proved. Interesting, isn't it? Now let us look at this proof once again. The first step is that you are going to take a square whose length of a side will be A plus B. So we know that the area of the square would be A plus B the whole square, right? And then in the next step, we are going to split the length, that is A plus B we have, right? So we are going to split that as A and B. So this will be the length of A and this will be the length of B, and then we draw 2 lines along the sides. So we have got 4 segmented areas, that is one is we have 2 squares and then we have 2 rectangles. Now let us try to find the area of these 4 figures. Here we know that this square is of length A. So the area of this square would be A square. And then this square is of length B. So the area of this square would be B square. And then we have 2 rectangles here where the sides are A and B. Here also it is A and B. So the area would be AB. When we add all the areas inside the square, we get the area of the whole square, right? So the area would be A square plus B square plus 2AB. Hence, the formula for A plus B the whole square is given by a geometric demonstration. Let us now look at another demonstration by Jeshtadeva. This is for the equation A minus B the whole square is equal to A square plus B square minus 2AB. For this, he is asking us to take 4 rectangles for which the sides would be A and B. So what would be the area of each of these rectangles? It would be AB, right? Now, he is asking us to arrange these 4 rectangles this way as shown in this diagram. This will create a small square inside, right? You can see the square. Now, when we arrange the 4 rectangles as shown in this diagram, we get a small square here, right? But then we don't know the side of the square. We will have to find that. How to find that? We know the sides of the rectangle to be A and B. And the same rectangles we have arranged it such that it comes into this shape. Now, we know that this length of this rectangle is A and this side it's B. So here also this would be A, and this part would be B. Now, when we subtract B from A, we get the side of the square, that is A minus B. So, to find the area of the square, it would be A minus B the whole square. Now, we know that the area of this small square is A minus B the whole square, and then the area of each rectangle is AB. But what about the area of this bigger square? Fine, let us see now. So, we know that the length of this is A and this length is B. So, we can say that the length of this square, this bigger square, is A plus B. So, the area of the bigger square would be A plus B the whole square. So, let us write it here. That would be equal to the sum of all the areas that is inside the square, right? So, that is A minus B the whole square plus 4AB. We already know the formula for A plus B the whole square, that is A square plus B square plus 2AB. Now, if we substitute this into this, then we get the value for A minus B the whole square, that is A square plus B square minus 2AB. Now, let us look at this demonstration once again. What does Jeshtadeva tell us to do for proving this equation? He says that we have to take 4 rectangles of sides A and B, and then you arrange it in such a way that we get a structure like this, so that we see that there is a smaller square that is formed inside. But then we only know the sides of the rectangles but not of this square. To find that, we see that the length of this rectangle is A, and then we see that this side is B. So, when we subtract this B from A, we get the value of this side of the square, that is A minus B. Now, we have values for all the sides of the square and the rectangle as well. Now, we find the area. So, the side of the square was A minus B, right? So, the area would be A minus B the whole square. And for each rectangle, it would be the product of their sides, which is AB. So, for each rectangle, the area would be AB. Now, if we see the outer square, we see that this length is A and this length is B. So, the area for the outer square is A plus B the whole square. Now, when we sum all these areas and then equate it to this area of the bigger square, it would be A minus B the whole square plus 4AB. When we substitute the value of A plus B the whole square, that is A square plus B square plus 2AB into this, then we get the value of A minus B the whole square, which is A square plus B square minus 2AB. The third demonstration that we are going to see is for the equation A square minus B square is equal to A plus B into A minus B. For this, Jeshtadeva asks us to take a bigger square which is of length A. So, the area of this square would be A square. And then we subtract a square whose side is of length B. So, the area of this square would be B square, and then we take this square, we subtract it. Then we get a structure something like this. Removing the area B square from A square, we are left with this shape. So we have two rectangles here. So we know that the side length of this is A. So if we have to get the length of this rectangle, then we are going to subtract this B from this whole A. Then we get A minus B. The same way here, this was A, right? And this side length alone was B. So the length of this would be A minus B, same is given here. Now, the rectangle that was here, we take it, flip it and put it above this rectangle. We already know that the length of this rectangle is A and this is A minus B that we saw in the previous slide. So, and we know the length of this to be B. When we put these two rectangles together, then this length would become A plus B because this is A and this is B. Now here this is A minus B. Then the area of this rectangle would be the product of the two sides, which is A plus B into A minus B. Let us look at this demonstration once again. For this, we are taking a square which is of length A, so that the area of the square would be A square. And then we are going to subtract a square from this bigger square, whose length would be B. So, we are going to take away a square which would have an area B square. Now that this B square being gone, we have the length of this rectangle to be A minus B. And anyway, the side of this rectangle is A. Then we take this rectangle, flip it and put it on the top of this rectangle. Now we know that the length of this is A and this to be B. So this whole length would become A plus B. We already know that the length of this is A minus B. Hence, the area would become A plus B into A minus B. So, A square minus B square gives us A plus B into A minus B. Now, let us look at this equation. A plus B plus C the whole square is equal to A square plus B square plus C square plus 2AB plus 2BC plus 2AC. Now, for this, we take a square where the length of the sides is A plus B plus C. So, along the lengths A, B and C, we draw lines, that is on two sides. This is A, this is B and C. And we see that we have got 3 perfect squares and then some rectangles, 6 rectangles. For these perfect squares, we know the length, that is, the length of this square is A. So, the area would be A square. The length of this square is B. So, the area would be B square. The length of this smaller square is C. So, the area is C square. Now, let us take these two rectangles. We know the sides to be A because the length of this side is A and this is B. So, the area would be AB. Similarly, the area of this rectangle would be AB, which gives us 2AB. Now, we have got the area for these 3 squares and these 2 rectangles. Let us take these two rectangles now. We see that the two sides are C and A for these two rectangles. This is A and C. Hence, the area of these two rectangles are AC. This gives us 2AC. The remaining rectangles are these two. We see that the sides are B and C. Hence, we get the area BC for these two rectangles. So, we get 2BC. Now, when we add the area of all the squares and rectangles, we get A square plus B square plus C square plus 2AB plus 2BC plus 2AC. We know that this whole side length is A plus B plus C. So, the area of this big square would be A plus B the whole square. Hence, we have got the geometric demonstration for this equation. Let us look at this demonstration once again. In order to find out A plus B plus C the whole square is equal to A square plus B square plus C square plus 2AB plus 2BC plus 2AC in the geometric demonstration, we are going to take a square whose length would be A plus B plus C. So, we draw lengths of ABC on both sides. So, we get geometric figures like these. Then, we find the area of each of the geometric figure that is inside. We have three squares here whose sides are of length A, B and C. So, we get the values A square, B square and C square respectively. Then, we find the areas of the rectangles. Now, we see that the length of the sides of these two rectangles are A and B. Hence, the area would be AB. The same way, for the other rectangles if we see, the areas are AC for these two rectangles and here we get BC. When we sum up all the areas together, we get A square plus B square plus C square plus 2AB plus 2BC plus 2AC. Now, we know the area of this big square to be A plus B plus C the whole square. Hence, the geometric demonstration for this equation is proved. Right from our introduction to algebra, we all would have come across these formulae. But then, look at this geometric demonstration. How easy and interesting, isn't it? And our Indian mathematicians have given these demonstration at the time of 1500 CE itself. To appreciate this and to understand these concepts better, take some charts and try to do these demonstrations on your own. Thank you. Dhanyavadaha.